All right, so here we are. Good afternoon, folks. And I have in my plans to discuss this antenna and what is happening with it. Like, for example, we have here that Tensor AD has a particular force being developed at it. It's about 1300 pounds, and we need to determine the tension on the other tensor as well, but also the force along the tower for this as shown here. So all that is kind of nice, but before we deal into this kind of a application, let me discuss a little bit the theory behind it. So let's see, and it has to do with this. Let me put my computer ready to write these things down. Let's see if I can get this right. All right, here we are. So what we have to deal is with the fact that we have three-dimensional forces in our Cartesian coordinates in the x, y, and z. So in order, and they are not coming from the origin. So in order to deal with this kind of forces, and we have to do what is said here: force vector directed along a line. So we need to indicate what is the position of that force with respect to 2 points, at least one point A and then one point B, and ensure that you understand the direction of that tensor, because it could be that way or it could be downward. So that's important, because according to what we have here, I'm going to write it here: the force in any x, y, and z direction will be equal to the force magnitude. That's a number. And then multiply by the position vector that is called r. In this case, I'm going to call A toward B, so it's going to be called AB, divided by the magnitude of that vector. All this here is called the unit vector, so I can simplify that by saying just F, the magnitude of F, multiplied by the unit vector called U. Alright, that is here. So let's say that U in this case will be a vector as well. So if we do that, then we can break any vector like this one that is not coming from the Cartesian axis. We can put it in terms of that. So for example, let's say that A is located here at a particular place on X, and we're going to call that X. Let's say that that value there is about parallel to the distance, is about let's say 2 feet, and then on the Z direction going up, we can say that that's about, let's say, 5. And now how about the Y direction? In the Y is 0, there's nothing, it is right at the wall Z and X. So what we need to do is to identify the position of that particular point, saying that it's going to be 2, 5, and oh, sorry for this, it's going to be 2 on the Y position is 0, but then on the Z position is 5. Now for B, we do the same. Let's say that B is moving along the y-axis a certain distance. Let's say that is here, and that distance, let's say that is 10 feet. So, and that's on the y. So now how about on the Z? On the Z, we'll say that is 10 as well, or 12, just to say a number. 12 going up. And now what about on the X? Now we can say that it's moving, it's not showing clearly here that it's moving this direction, but let me make it, so that it has a direction moving towards the X. And let's say that it's about 2 feet as well, but moving like this. So we're going to write 2 feet here. So now we have the position of each point A and B, and what we need to do is to apply what is called the position vector. What is the position vector? Now take the direction that is we are moving from A to B. So by doing that, the position vector is equal, now the position B is 2 minus the position at point A. That's on the X. On the Y, it's going to be 10 minus 0. Then on the z it's going to be 12 minus 5. You see, it's important to understand where we're moving. We are moving from A to B. So A is going to be on this side of this position vector, and the B is the beginning, is the end of the point. So it's sort of like a delta. Now with that said, then the position vector A, B is equal 2 minus 2 is 0, 10 minus 0 is 10, and then we have 7 here, and we finish. Now that's the position vector. We need the unit vector AB. In that case, the unit vector is, we can write 0, 10, 7, but remember that this needs to be divided by something, and that something is the magnitude. We're going to get the magnitude here, the magnitude of AB, which in this case will be 0 squared plus 10 squared plus 7 squared, the square root of all that, and then we have equal 0 squared is 0 plus 100 plus 49. So it's the square root of 149. And so let me pull the calculator here, and that will be 12.2. So the idea of our unit vector is divide that by 12.2 along every axis. Now we have the position vector. For some reason, we know already F has a magnitude already, like, you know, we can say that F equal, let's say, 200 pounds. How would be the distribution of that magnitude of that force of the 200 pound in the axis X, Y, and Z? For that vector F will be 200 times the distribution, in this case in the X axis is 0, I have nothing there, but then on the other axis, like in the Y axis, it's going to be 10 over 12 by 2 and 7 divided by 12.2. So if we break down this magnitude of 200, F will be 200 and 0, that will be 0 on the X position, let's call that I, and then plus 200 times 10, 12 divided by 12.2, plus, and that's on the J, and plus 200 times 7 divided by 12.2, and that's going to be on the K. So this is basically the distribution of our vector, in this case that force of 200 pounds, which we said is going to be like this one. How would that be? And as shown, there's no force or tension on the X, because the point started at the same point, like 2 feet here, but point B is also at 2 feet, so there's no movement from the X direction, so that's why the force ends up being 0 on the X direction, but then we have this on the Y and Z direction. Well, that's basically the idea of how we deal with forces that are not directly on the origin of this Cartesian coordinate. So now let's apply this knowledge to our problem. So let's go back, now that we understand this about forces directed along a line. So let's go back. How can that help us to understand this problem better? So that's what we're going to do now. Hold for a second here. So the first thing that we do is, what is the point here that is common to everybody? That point is A, because everybody is touching A. So that's a very important point, and we gonna do is get the coordinates on the x, y, z for that point A. But before doing that, let's do what we call a free body diagram. So that point A, what's going on here? So it seems that there's a force on the D tensor going this way, but there's also a force going this way on the B. But there's also another force, let's throw it like this, going to Z. But then what's going to happen with point A and this 3 tensor is going to be pushed down. So this from E to A, the force needs to be up to maintain that point where we want it. So this is the direction of that force in the antenna. Basically, it's going from E, but it's going from E to A, and this is point A. On the other cases, the other tensors, like for example, from A to C is coming down, from A to B is coming down, and from A to D is also coming down. So that's very important, because now we can start to, work our position vector. But first of all, let's get the coordinate of A, B, C, D, and E, just to work on that. So the position for A will be like, where is A? That position A is 0 on the X, because it's exactly right here, but it's also 0 on the Y, but it's 30 feet up. So that means that it's 0, 0, 30. And what about B? B is right at the position here. It's going 10 on X. As you see, this is parallel to this, so we know that it's going 10 on X, but it's also going on the negative direction of the X, or in this case of the Y direction, and it's going 15 feet, so that's negative 15. Don't forget the negative sign, or this will be screwed up. Now, that position, that vector B, is right at the 0 position of Z, meaning that we are here in 0. That's AB. How about C? Well, sorry for this, let me write this better. The C position will be, let's see, it's going, let's see, where is that C? That C is going that way, minus 10, but that's on the Y. How about the X? Oh, here's the X. You see, it's parallel, this line is parallel to this one, so it's going minus 15. It's going minus 10. This 10 goes here, but it's also at the position on Z that is 0, so it's 0 here. How about ABC? That's D. Now D is located at the position, let's see, in X. It's not moving back and forth, it's not, so meaning that it's on 0 here, and it's how about let's see, on the Y is clearly set 12.5 this direction, so it's 12.5, and it's also at the 0 position. Perfect. Now here's the story. How about the position E and why we need it? Because basically there is a vector that is moving from E to A, so there's a force on this antenna member that we need to deal with. So let's locate that here. So that's 0, 0, 0. Perfect. So now we have the free body diagrams right here, but we also have the position of each point to locate our position vector. So now let's work on our first position vector, which is going to be let's say let's work with AD. The letter A here is where we start and the D is where we end, and that's important because when we do the math, we want to be sure that we put this right. Like for example, that would be on the first point, it's going to be 0 minus 0, so it's 0, sorry, we are talking about this guy and this guy, so it's going to be whatever is in D, 0 minus 0 is 0, and now 12.5, oops, I let lose a letter here, A, B, C, D, So it's going to be 12.5 minus 0. That's 12.5. And that's going to be 0 minus 30. So that's going to be minus 30. There we go. Now, and what else we need here? We need the magnitude as always. So let's work out the magnitude. The magnitude will be everybody square. Just for the sake of the argument, let's put the 0. The 12.5 and the minus 30 plus minus 30 square. Remember, minus 30 squared, that would be a positive number. And eventually, let me pull the calculator here, and that will be let's see, 32.5. So we got the magnitude. That 32.5. Let me write it down here. That's gonna be ART magnitude 32.5. All right. So now the next position vector is going to be RAC. Again, we are moving from point A to point C. It's being pulled down, so that means that what we are looking now is this guy and this guy. So that's going to be minus 15, minus 10, and minus 30. And we do the same and we calculate the magnitude. So the magnitude is minus 15 square, minus 15 square plus minus 10, be careful here, minus 10 square, and plus minus 30 square, and that will be that the magnitude of that position vector is calculator here, 15 square plus the square root of all that, 35. So we got that as well. Now, how about the other position vector? It's called in this case gonna be A, B. Again, we are talking about the difference between these two guys. So that means 10 minus 0 is 10, minus 15 minus 0 is minus 15, and 0 minus 30 is minus 30, and the magnitude here is gonna be actually, this, you check this number and you check this number, they're the same except in different position. But if we are talking about the magnitude, it's easy to figure it out that the magnitude of that vector, of that position vector, is just gonna be 35 as well. No problem there. All right, so now we need another one, which is the end of this, that is this the one that is across the antenna, and that's moving from E to A. And now be careful with that, because we are moving from E to A, meaning that E is the beginning, A is the end. So it's gonna be we're talking about this guy, but this guy is the beginning, so it's gonna be this one minus this one. So the first one is 0, the second one is also 0, but 30 minus 0, that would be 30. Now it's interesting, the magnitude of this guy is obviously 0, 0, so it's gonna be 30 square. The square root is obviously 30. We are back into business. So that's basically what we have, and that's the decomposition of this vector, the unit vector. Now we need to do the math, and the math is that we need to add all these tensor in the x, in the y, and the z, so that we get this properly, all the numbers right. Now the first thing that they provide us is they say, you know what, there's a particular tensor that is called the cable AD, A and D, that is already pulling with 1300 pounds. What that really means, it really means this, that TAD as a vector is going to be equal to the magnitude of TAD of that tensor multiplied by the position vector of AD divided by the magnitude of that position vector. In numbers, that means they already gave us this number, which is about 1300, so we write it down. And this divided by this is basically take this number here, those has to be 0, 12.5, and minus 30, and divide each one by the magnitude. In this case, 32.5, 32.5, and 32.5. And you have the distribution of this tensor in X. Well, let's write it like this, like I, J, and K. All right, so we can certainly do that to the others, and all the distribution that we had, like for example, how about TAC? TAC, I'm gonna write it close here so this start to look better. So TAC as a vector is equal to the tensor, which I don't know what it is, the number, TAC. Now again, we do the same. So we take the position vector, which is minus 15, which is minus 10, which is minus 30, and we need to divide that by the magnitude. And the magnitude of that guy is 35. So we divide this by 35, by 35, and by 35. We close here. So that we have TAD, TAC vector, and we do the same with TAB, and that would be the magnitude of TAB. I'm not putting this like this. I could certainly do that, but this is a vector, meaning that has position x, y, and z, but this is magnitude. All right. So again, TAB, that will be 10 minus 15 minus 30, and all that need to be divided again by the magnitude, and that would be 35, 35, 35. Close here. And the last one, which is called TEA, equal TEA time. Now this is interesting because this is 0, this is 0, but this is 30. Now, but you're dividing by 30, right, everybody? So eventually this end up being TEA only on the K position. So TEA 30 over 30 is 1, so we end up like this. Be sure that you understand that this is only count on the Z position. All right, so we get that, and we are pretty much done here, except that we need now to do for equilibrium. You know that the sum of all the forces in X equals 0. With that said, let's find the first one. Like for example, this 1300 times 0, there's nothing on that particular position, but I'm gonna write it down. So if I do that, that's gonna be 1300 times 0 divided by 32.5. And now here's a negative, so it's gonna be minus TAC 15 over 35. And how about here? TAB is a positive, so plus TAB, and that's going to be 10 over 35, and that's equals 0. That's what we got. This is 0, and we are done with the balance on X. How about the balance on Y equals 0? Let's see. That's the everything that is on the J position. All right, and that would be the 1300 start to make sense now. So we're gonna be 1300 times 12.5 divided in this case by 32.5. all right, and now we move to the other one, so it's gonna be plus, that's a variable, TAC times, in this case gonna be minus 10 over 35. And now we move to this guy plus TAB So it's negative, so write it down. Don't get screwed. Don't screw these numbers. Over 35. And now how about the TEA? There's nothing here. It's 0, so equals 0. There's nothing more on that equation. How about on the C position? Let's see, equals 0. On the C, so we have this. So we have a number there, 1300 minus 30 over 32.5, and that's the ACDs. And how about TAB? TAB, in this case, let's see, that one, we got that, and then we need to put TAC, and that TAC will be plus TAC minus 30 over 35, and now we are moving now to TAB plus TAB. Oops, sure that you write the letters right. Let me rewrite this because it doesn't look good. TAB, there we go, and that's going to be minus 30 over 35 as well, and we are in the last one now, plus TEA, and that's equal 0. So that's basically it. The distribution of all the forces, on the X, Y, and Z. And what are the unknowns? The unknowns are TAC. I don't know what it is. TAC, TAB, and TEA. And all these three variables are the unknown. But it's interesting. The fact is that we have three equations, three unknown. That makes life easier. We don't have to make any assumption, and the problem can be solved straightforward with the information just provided. That they already provide a tension on the tensor A toward D. So this is basically like this. All right. With that information, what we need to do is to start solve this system, and let's see where we go with it. In the first case, and very straightforward, if we look into the balance of fx, we have two variables here. Definitely we can put one in terms of the other. The nice thing is that the second equation, the balance on fy, include both of them, only two of them. So see, with these two equations here, we can solve for TAC and TAB because there's two unknown and two equations. Now on the third equation is good enough to get then the final variable, which is the tensor EA, or the force that is on the antenna or the tower. Let's see. So for the first case, we got that TAC on the first equation. TAC must be equal, let's write it like this. Like for example, if we take this to the other side, so it's going to be positive. I'm going to write it here. TAC 15 over 35 must be equal TAB 10 over 35. So TAC is equal TAB 10 over 35 times 35 over 15. So the 35 cancel out, and we finally have TAC is equal TAB 10 over 15. We can simplify that if we want to, but it's enough, or just saying that TAC equal TAB. Let me get this in decimal places. That's what's that? 0.67. That's good enough. All right, so we have that. Now what we need to do is to substitute this guy on our second balance here on the force on y, and we got 1300 12.5 divided by 32.5 plus TAC, and that TAC, and we already know what it is. TAC is TAB times 0.67. Careful with the negative sign here. Minus 10 over 35 plus TAB minus 15 over 35, and that's equal 0. So this is going to be negative, and this is going to be negative, so this can go this way. And let's get the calculator here, and this is going to be 1300 times 12.5 divided by 32.5. That's about 500 equal. Now this is gonna go to the right side, so TAB is our common factor if we use the distribution rule here. So we end up 0.67 positive 10 over 35 plus positive 15 over 35. So that means, let's see where, that TAB is equal 500 divided by this guy here, and that's about 0. Okay, point approximately to decimal places 0.62. So that means that TAB is about 106.45, and that's pounds. All right, so we got TAB. That means that whoops, did I got this right? Yeah, I got that right. So that means that TAC, remember, TAC is right here, is based on TAB 0.67, so that means 806.45. That's TAB times 0.67, and that will be 540.32 pounds. So we got, we got two of those forces, and the thing that is left is to resolve for TEA, and that will do. Now this is negative, this is negative, this is negative, meaning if I take that equation, let's do it here, meaning that TEA is equal to let's write this down here. So it's going to be 1300 minus, positive now, because everything here was transferred to the right side. So it's going to be TEA equal 1300 plus 30 over 32.5 plus TAC. What is TAC? TAC is 540.32, and that's going to be 30 over 35 plus TAB 106.45, be sure, 106.45, 30 also over 35, and did I got all of them? Yeah. And that's basically the answer here. TEA equal, let's see, what would that be? 1300 times 30 over 32.5, that's 1200 plus, I can take this as a factor, it's a common factor, so you can add these two together and then multiply by 30 over 35, and that would make life easier, like this. This is what I'm saying. that should provide the final result as well. All right, so we got this. So that's about, all right. So the final result is, oops, let me write this right, is 23,154.37 pounds. So that's basically the force through that member. Now, take a look at it. They are both, all of them are positive. Like for example, TAB is a positive number, end up being a positive number, and so TAC, and so TEA. Meaning that when we did our free body diagram, the direction of the vector were presumed correct, and that's very important. It happened that some of these results end up being negative. It means that probably the direction of the vector is incorrect. Well, that's more than enough. That's an application again of this concept about when we don't have vectors that are coming from the origin, but you can still work the magic around it using position vector and make life easier, because in life basically this is basically what we have most of the time, and so we need to work it out as per this procedure. Have a great day. Bye.